Welcome to the first in a series of videos detailing the Corr Instruments corrosion monitoring product line. Chapter 1. Principles of the nanoCorr corrosion monitoring system. nanoCorr is the world's first commercial system for corrosion monitoring based on the coupled multi-electrode array sensor CMAS technology, which was initially developed in an internationally recognized research institute by a team led by an engineer who founded Corr Instruments. nanoCorr is backed by 3 patents licensed from an internationally recognized institute and an additional 5 improvement patents wholly owned by Corr Instruments. CMAS technology is suitable for monitoring non-uniform corrosion, including localized corrosion such as pitting corrosion and crevice corrosion. The principle of the technology is best described by the following diagram.
As seen in the diagram, the upper image illustrates a piece of metal undergoing localized corrosion, pitting corrosion caused by a corrosive electrolyte. Electrons are produced at the corroded area or anodic sites due to the oxidation and loss of metal. The electrons of this piece of metal are flowing internally from anodic sites to cathodic sites. If the electron flow can somehow be controlled, i.e. forced to flow along a known path, electrons can be counted or current can be measured along the known path. CMAS technology is implemented by cutting the metal into small electrodes approximately 1 mm in surface diameter and insulating each electrode with an epoxy or ceramic insulation. Each electrode is coupled to a common joint through a ZVA, zero voltage ammeter, so that the current flow through each electrode can be measured and quantified. Due to the small surface area of the electrodes, the corroded electrodes simulate the behavior of a single pit, and the current from the most corroding electrode can be used to calculate the maximum penetration rate, and charge from the most corroded electrode can be used to calculate the maximum penetration depth. CMAS probes are pictured in this image and can be manufactured with 9, 16, or 25 electrodes. The electrodes are machined from the type of metal being utilized in the client's process, and for special cases, the client can send Corr Instruments a sample of their metal to be machined into electrodes such that the composition of the electrodes match the composition of their metal. The CMAS probes can be manufactured to a variety of insertion depths, and due to the length of the probe itself, the life of the probe can be up to 20 years or more, depending on the corrosion rate the probe is exposed to. To use the CMAS probe in multiple solutions, the probe can be sanded or grinded down until the corrosion product or corroded electrodes have been removed, resulting in clean electrodes. The probe could then be placed in a new solution without measurements being affected by the probe's corrosion rate exposure history. Many clients refer to the CMAS probes as electronic coupons, due to the probe's capability of delivering real-time corrosion rate measurements. This is a key advantage of the CMAS technology, the ability to measure real-time corrosion rates and provide the client with constant feedback concerning the corrosion conditions in their process. This can be utilized for such applications as inhibitor dosing, where real-time measurements can correlate the inhibitor concentration to the corrosion rate fluctuation after dosing has occurred. Many articles have been published concerning CMAS technology. For any further information or details, please refer to corrinstruments.com or view one of our videos linked on the website or searchable on YouTube. On this slide, a carbon steel CMAS probe is depicted that has undergone localized corrosion from exposure to drinking water for 10 days. Corrosion product can be seen on these electrodes, and after cleaning, pitting can be seen on the corresponding electrodes due to the localized corrosion. In this slide, we compare a CMAS probe after 5.5 months of testing to a coupon inserted into the same environment. After cleaning the corrosion product from the CMAS probe, as seen in this image here, the maximum penetration rate was measured to be 149 mil per year. From the coupon tests, The maximum penetration rate was calculated to be between 100 to 200 mils per year. The 149 mils per year calculated from the CMAS probes correlate with the coupon tests that show 100 to 200 mil per year corrosion rates. This is referenced from NACE paper number 04077, published in 2004. This slide depicts corrosion monitoring in oil-water cooling systems in aluminum rolling plants. This image depicts the interior of a piping structure and the orientation of the CMAS probe. CMAS probe can be manufactured to a variety of insertion depths, such that the probe can be either flush with the pipe wall or can be intruding into the inner area of the pipe. This is an example of the CMAS probes in a chemical process stream. As we can see here, the probes are in the chemical process stream through a fitting, an MPT fitting. And the nanoCorr is in an enclosure required for field use. In some cases, for intrinsically safe field use, the nanoCorr must be placed in an explosion-proof container. The current slide shows how the CMAS corrosion probes can be used to measure soil side pipeline corrosion. In this example, the probes are inserted into soil sample with the laboratory analyzer A50 to measure the corrosion rate of the soil side of the pipe.